Hey everyone, exciting news. We've got a theme song now.
Oh, wow.
Yeah, all about machine learning,
Really?
composed by yours truly.
Wow, that's amazing.
I know you're probably thinking, "What?" But trust me, it's pretty catchy. You can check it out after this deep dive.
Awesome.
Speaking of deep dives, some recent lectures I've been listening to got me thinking about this deceptively simple but incredibly powerful concept, sampling. And guess what? We're diving right into it today.
Sampling. Yeah, it's funny how it often gets overlooked, right?
Exactly.
Because it sounds so basic, isn't it?
I was thinking the same thing.
But as we'll see, it's really the foundation for some truly mind-blowing applications in machine learning.
Sampling, isn't that just picking a few things at random? But it's so much more than that. In the world of machine learning, it's like this secret weapon for unlocking insights from massive amounts of data.
Yeah, think about it. Analyzing data sets with millions or even billions of data points is incredibly resource intensive. Sampling allows us to work with smaller, more manageable subsets while still getting a remarkably accurate understanding of the whole picture.
So we're essentially saying that we don't need to analyze every single data point to get the gist of what's going on. A carefully chosen subset can do the trick.
Precisely. And one of the core principles behind why sampling works so well is the law of large numbers.
Okay.
As our sample size grows, the average of those samples gets closer and closer to the true average of the entire population.
Okay.
It's a pretty powerful concept when you think about it.
So let's unpack this. If we wanted to know the average height of everyone in the U.S.,
Yeah.
it would be practically impossible to measure every single person.
Right.
But with a large enough sample, even if it's a fraction of the total population, the average height we calculate from that sample would be a pretty good estimate of the true average, right?
That's exactly right. And here's where it gets even more interesting. The implications of the law of large numbers go far beyond just calculating simple averages.
Okay.
It allows us to use sampling to approximate integrals, which are these mathematical tools used to calculate things like the area under a curve.
Hold on a second. How does averaging a bunch of samples connect to solving integrals? That seems like a pretty big leap.
It might seem counterintuitive, but bear with me. When we have a probability distribution,
Okay.
which describes the likelihood of different outcomes,
Right.
we can use integration to calculate important statistical measures like the mean and variance.
Okay.
But thanks to the law of large numbers,
Right.
we can also approximate these same measures by simply averaging values from our sample.
So we have two paths to the same destination: complex integration or straightforward averaging. And both can get us pretty close to the real answer.
Exactly. And that's just the tip of the iceberg. We can leverage sampling to unlock a whole world of possibilities in machine learning. It's not just about saving time and resources. It's about using smaller data sets to gain insights that would otherwise be computationally expensive or even impossible to obtain.
Briefly, Professor Wu touched upon this.
Yeah.
But it's not just about calculating means and variances, right? We can use sampling to do things like generate our own data.
Yeah.
That's where things start to get really wild.
Absolutely. We can essentially create synthetic data that mirrors the patterns and characteristics of our original data set. Imagine the possibilities. We can generate new data points that never existed before, all based on the probability distribution learned from the original data.
Wait, so we're talking about creating something from nothing. Give me an example, let's say. Generating images of cats.
Perfect example. Let's say we have a data set of cat images. We can use this data to learn the underlying probability distribution of cat features, fur patterns, ear shapes, eye color,
Right.
the whole 9 yards. Once we have this distribution, we can use sampling techniques to generate new cat images that have never existed before. It's like having a magical cat creating machine.
Okay, now you've got my attention. What kind of sorcery are we talking about here? I'm ready to hear more about these sampling techniques.
Well, there are several fascinating techniques, each with its own quirks and advantages.
Okay.
One of the most intuitive is called inversion sampling. Imagine you have a function and its inverse. The function takes an input and gives you an output. The inverse does the opposite. It takes the output and tells you the corresponding input. Pretty straightforward, right?
Yeah, I get that.
Yeah.
But how does this tie into generating those never-before-seen cat images?
Here's where it gets really cool. With inversion sampling, we essentially use the inverse of the cumulative distribution function, or CDF, of our cat image distribution to generate new samples. We generate random numbers between 0 and 1 and plug them into this inverse CDF, the output, a brand new sample from our cat image distribution.
So we're kind of reversing the process to create new data points based on the probability distribution. Mind-blowing. But what if we can't easily find the inverse of that distribution? What then?
That's where another clever technique comes in, rejection sampling. It's a bit more involved, but the key idea is to propose a simpler distribution that we know how to sample from something easier to work with, like an exponential distribution.
Okay, but how can we use a simpler distribution to generate something as complex as a cat image? It doesn't seem possible.
That's where the rejection part comes in. We first generate a sample from our simpler distribution, and then use a set of rules to decide whether to accept or reject it.
Okay.
The acceptance criteria are based on our target distribution, in this case, the cat image distribution. By selectively accepting or rejecting samples, we ensure that the accepted ones approximate our target distribution, even though we started with something much simpler.
So it's like we're filtering the samples from the simpler distribution to match the characteristics of our cat images. That's really clever. I'm starting to see how powerful this can be.
Exactly. Rejection sampling is like a sculptor chipping away at a block of marble until the desired form emerges. It's all about refining and shaping our samples until they accurately represent the complex distribution we're aiming for. And believe me, there are even more techniques where that came from.
Wait, there's more. I'm already hooked. Tell me everything.
There's a whole family of sampling techniques out there, each with its own strengths and weaknesses.
Yeah.
But before we dive into more,
Yeah.
I'm curious, what about the idea of rejection sampling stands out to you?
You know, it's that idea of starting with something simple and then refining it to match something much more complex. It's like sculpting with probabilities.
That's a great way to put it.
Yeah.
And it highlights the ingenuity of these techniques. We're not always limited to working with the exact distributions we need. We can get creative and leverage simpler tools to approximate the results we're after.
So you mentioned there are even more techniques.
Yeah.
What else is out there in this sampling toolbox?
Well, there's one called kernel density estimation, or KDE sampling, that I think you'll find quite interesting.
KDE sampling. Hit me with it.
This one leverages the original data points to create new ones. It's like each data point is a seed that sprouts a cluster of similar data points.
Okay, I'm intrigued. Walk me through how that works.
With KDE sampling, we start by randomly selecting a data point from our original data set.
Okay.
This data point becomes the mean of a Gaussian distribution.
Gaussian distribution. It rings a bell. Isn't that the bell curve thing?
Yes, exactly. It's a very common probability distribution that pops up all over the place in statistics.
Right. Okay.
We then use this Gaussian distribution, centered around the chosen data point, to generate a new sample. By repeating this process, we can create a whole new data set that reflects the characteristics of the original data.
So we're essentially taking each data point and using it as a starting point to create a little cluster of new similar data points. It's like we're building a probability cloud around each original data point and then sampling from within those clouds.
That's a great way to visualize it. And this technique can be particularly useful when our original data set is small and we want to generate more data points that follow the same patterns. It's like giving our data set a little boost.
You know, I'm starting to realize just how much sampling is at the heart of these generative models we keep hearing about. The ones that create those hyper-realistic images of people and animals that don't actually exist.
Right.
It's like they're weaving together samples from some fantastical probability loom.
That's a brilliant analogy.
Yeah.
And you're right, sampling is absolutely central to how these generative models work. These models are trained on massive data sets and learn to represent the underlying probability distribution of that data. They become masters of the data's inherent structure and patterns.
So they're like these supercharged probability wizards churning through data and conjuring up new creations. But how do they actually translate that knowledge into creating those stunning images? Where does sampling fit in?
Well, once a generative model has learned the probability distribution of, say, human faces, it can generate new faces by sampling from this learned distribution. Each sample represents a new combination of facial features that the model has never seen before, yet it still adheres to the rules of what a human face can look like.
So it's like the model has absorbed all the information about what makes a face and is now using that knowledge to dream up entirely new faces. That's incredible.
Who knows what amazing applications and creations await us in the future?
That's the exciting part, isn't it? The journey of discovery never truly ends. So to our listeners, keep exploring, keep questioning, and keep diving deep into the world of machine learning. And who knows, maybe you'll be the one to unlock the next groundbreaking application of sampling. Until next time.